Sounds good. Yeah, thanks to Quinn and Max for inviting me to give this talk about the Buffon needle problem. And as you'll see, there is a subtitle which says "A Glimpse into Continuous Combinatorics." So the goal of this talk is not only to address this problem, whatever it is, which I'll be describing very soon, but also to see where this kind of like thinking leads us into. Like there are many different solutions to this problem, but we'll be focusing on one particular solution. Yeah. So yeah, this is the Buffon needle problem. You have like a floor made of parallel strips of wood and equidistant, so each with same width d. And what you do is you can either take a bunch of needles and throw them randomly. So that's one way to do it. Or you could start with just one needle and and pain yourself and keep doing this experiment all like again and again. But whatever be the case, what you do is count the number of intersections, overall intersections with these lines that are there, like joining the two adjacent strips of wood. So the question that is being addressed here is, what is the probability that the needle will intersect a line between two strips? That is, it will not completely lie within a strip. For example, the ones that have been circled, those needles are the ones that have cut across a line, but the remaining three, they lie exactly within a strip of wood. And this probability effectively you can think in terms of a frequentist way, in the sense like if you threw like 10,000 needles, you want to count like maybe there's like 2,000 of them, and then your probability would be like 1/5. So that's the way you should interpret this thing. All right, so before we get into a solution to this problem, like computing this probability, if you had the time to go through the abstract I had sent out, I said like we will be computing pi in a very inefficient way using this kind of physical experiment. So I'll be talking a little bit about pi, and then we'll come back to this problem. Yeah. So yeah. So here I say, okay, surely the population has nothing to do with the circumference of the circle. And usually in statistics and so all, like you must have encountered something like a bell curve or a normal distribution and so on. And there, the density, like these kind of things with a peak near the mean and like some sort of exponential decay at the tails. You have this density which has a pi term in it, 1/√2 pi sigma squared. And then usually people write it as e to the minus x squared over 2 sigma squared. But I have tried to rephrase as 1/e. It's exactly the same. E inverse is 1/e. But I had a reason for doing that. That's because 1/e is something you can write as 1 minus 1/1 factorial and so on. So pi, for example, is the ratio between the circumference and the diameter. And whereas 1/e you can think of as, like if you restricted this series at k, then that would be if you had a set having cardinality k elements in that set. So the number of permutations you can do are k factorial, right? And this number is exactly the proportion of permutations which do not leave anything invariant. Like for example, you could have a permutation where you left one alone and permuted the rest. So such a permutation is not allowed. So derangements are those permutations which do not leave anything, some sort of like invariant. So in that sense, this is a weird kind of thing. Like pi has a meaning, circumference times diameter, and so on. And somehow they come together to illustrate this thing about like statistics and so on. And I actually stole this phrase from an essay by Eugene Wigner, who was actually a Nobel laureate in physics. And he wrote this essay called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. And he starts, this is literally like the first paragraph, and I have taken some liberty in paraphrasing a couple of his sentences because it wouldn't fit in this slide. So, but overall, this was the first paragraph where he starts with a kind of anecdotal or apocryphal joke kind of thing, where he says there are two friends, there's one of them is a statistician, and he shows this, oh, I'm doing research on population trends and so on, and this is a Gaussian. And he asks, oh, what's this pi doing here? And then he says, oh, this is how it works. And then the classmate says, oh, well, now you're pushing your joke too far. Surely the population has nothing to do with the circumference of the circle. So all this to say that like there's a remarkable unity between different branches of mathematics. So like if you try to deconstruct every bit of it, then it might seem weird that one really has some sort of weird connection to another, but like that's the way it works. And if you feel like a random experiment like the needle experiment I said could actually kind of tell you what the value of pi is, then this is what we're talking about. But yeah, before we begin the main meat of the talk, I'll just tell you that if you really want to be computing digits of pi, then you should not probably use this method. There are much better methods to compute the value of pi. And for example, a very slow converging series is the one I have right in, like the first is 4 times 1 minus 1 over 3 plus 1 over 5 minus 1 over 7 with all these odd numbers and alternating signs. But this converges as a log of n, which is a very slow growing function. But you have also other formula like Ramanujan's formula, which is pretty remarkable how he found it. But anyway, like presently, I think there are a few theories about like deriving such formulae, like not just this particular one, but like a family of such formulae. But it took a long time to really figure out why these things really existed. But yeah, I mean, and again, I have the super fast converging series. So if you really want to compute digits of pi, you should not be really doing this physical experiment, but it's fun. It illustrates a kind of point of view, which is the main theme of this talk. Okay, so let's get back. Before we approach that problem, just to remind you, so let's say you do some sort of random experiment, like throw a die or like toss a coin or maybe 2 coins. So a random variable is a numerical description of the outcomes of such a like statistical process. So essentially like you do some experiment and then it assigns a number to what the outcome is. Like for example, I say like how many heads will occur in a series of 20 flips of a coin, like fair or non-fair, like depends on what like model you have, but this is an example of a random variable. More formally, you can think of it as just some function that assigns a number to each event that happens. Like for example, maybe you roll 2 die like together and you see like 3 on one and 5 on another, and maybe the random variable you have is the sum of the two, so that's 8. So this event that like you roll a 3 and a 5, the number you get out of this event is 8. And for a random variable, you can talk about the expected value or average value. And another way to think of this expected value is like you have this random statistical process. You keep repeating that like maybe 1,000 times. And each of these times you notice a value of the random variable. Then you just add them up and divide by, I forgot like what number I said. Maybe I said 1,000 times. So you divide by 1,000. So that's what the average value is. And that's exactly what the expected value is. So you define an expected value of a random variable as the value it takes and times the probability of like taking that value, and you sum them up. Like if you try to think intuitively, like for example, let's say you have like a binary kind of random variable. It only takes value 0 and 1, and one of them has like, let's say the value of 1 has 90% probability and the value of 0 has like 1%. So when you kind of like keep repeating this experiment, you expect that the average will be about like 0.9, because like 90% of the times you see a value of 1 and 10% of the times you see a value of 0. So if you did the math, you would see that the value is like 0.9 times 1 plus 0.1 times 0, which is 0.9. So that's the expected value. All right, so random variables and expected values will be kind of the tools we'll be using to solve this problem. In fact, like solving this problem in a conceptual way rather than like doing some hard computations of what the probabilities are. All right, so what's the random variable in our problem? So if you have a needle of length L1, so I throw this needle on the ground and I notice the number of intersections. That's a random variable. So this is the statistical process I'm doing, throwing needles. And the number I'm getting is the number of intersections. So this is actually a positive, or rather I should say non-negative integer value random variable. It takes values 0s, 1s, 2s, and so on. Those are the only values it takes. And so if we don't know what really the probabilities here are for like intersecting n times, but let's call that number Pn, then this expectation, like the average number of times it intersects, is equal to um, this formula we have, which is summation n times Pn. It's exactly the same formula we had in the previous slide. But in one particular case, where the length of the needle is actually less than the width, which means it cannot really span a whole strip. Like for example, if L1 were slightly bigger than D being the length of the width of the strip, then you could be at right angles to that and intersect twice. That could happen. But if the length of the needle is strictly smaller than the width of the strip, then the only values X1 can take are 0 or 1. So here you can explicitly write it out saying that, okay, expectation of this random variable, expected number of intersections, is actually just the probability of intersecting once. So, remember, in the Buffon needle problem, we are interested in this probability P1. How many times does it intersect? So for the case of L equals D, this probability P1, like the question of finding this probability P1, is exactly the same as like computing this expected value, this average value of this random variable X1. All right, so any questions so far? Okay, I don't see any in the chat box. All right, yeah. So now, yeah, so a lot of the times, like this is another like kind of theme I will stress on it that goes on in mathematics is, and also in other parts of science, which is called the inventor's paradox, which means that sometimes to solve an easy looking, very specialized problem, it actually helps to look at a harder problem, like a more general problem, which captures the exact kind of like spirit of the problem. Like if it is too specific, it actually might be much harder because you are not able to exploit the nature of the problem, the symmetries and so on. So we will actually try to solve a harder problem, like not just rigid noodles, which are straight lines and so on, but actually noodles. So this is also called the Buffon noodle problem. And the very interesting fact is that if you, instead of like having a straight needle, if let's say you bent it, like at some point you bent it, like the length is still the same, and it's, let's say it's like two smaller needles soldered together, like welded together or something, then and each of them you think of as two different random variables, X1 and X2. So if there were two separate needles, of course they're independent, so you can just add things up. So expectation of X1 plus X2 would be expectation X1 plus expectation X2. But the beautiful fact about expectation is actually additive, irrespective of the fact whether X1 and X2 are independent. And let me remind you what independence really means. So we say like X1 and X2 are independent. If I tell you the value of X2, you should not be able to say anything about the value of X1. That's what it means to be independent. Like for example, if I had two separate needles of length L over 2, instead of one like needle of length L, like, and I threw one and then I threw the other, like knowing that the first one intersects like at one point doesn't really give you any information about like how the second one intersects. But if I welded them together, and so you can actually cook up special cases where definitely knowing that like one of them intersects like tells you that the other does not. Like maybe you soldered them at right angles and your width was the right the right number and so on. So clearly they're not independent. They're very much dependent random variables. But this average value, it's simple mathematical fact that expectation is additive. So that's what you have. Expectation of X1 plus X2 is expectation of X1 plus expectation of X2. So what essentially that means is if I just took this new figure I built, which is not really a straight one, but this like twisted kind of figure, and I threw it, so the number of intersections will be just the sum of the number of intersections of the smaller components. And and the same holds if you go for more than two, like K noodles shouldered together. And you have the same formula, expectation X1 plus expectation X2 and so on. So what this tells us is that this expected value is actually only dependent on the length of what you have. Like even if you take a polygon of the same length, doesn't matter how it's shaped, actually polygon means it's closed, but like just think of as a piecewise joined like needles. And so the orientation doesn't matter really. So now we can set this problem in the following manner, that so the expectation of x, as I said, is just a function of L. It does not depend how like the needles are arranged together. As long as the length is L, this is the number of intersections you will have. And note that, so what are the basic properties of F here? First of all, F has to be a positive number because it's just a average value of positive things. Like we are counting how many times things intersect. So that's an average value of positive things. And another thing we know is if we have a longer needle, like the chances of really like intersecting those lines is going to be higher. So in that sense, we know that F is actually an increasing function of L. And the third thing we know is this additive property. And how do we figure? That's because a big needle of length L1 plus L2, you can just pretend that it's welded, like it's made up of two needles, one with length L1, another with length L2, and you have just shouldered them together in a straight line. And going back to the additivity of the expectation in the previous slides, you have this additive formula. F of L1 plus L2 is F of L1 plus F of L2. So now we have to figure out what this function F is. And yeah, this is something like which you may have seen, and like this I think it is called something like Cauchy's problem. Like this is a functional equation you want to solve. So you start plugging in a few numbers. So first let's plug in integers because it's easier to write them as sums of 1. So f of n is actually f of 1 plus 1, you add n times. And then using the basic property 3, we split this sum up. And so that is f1 plus f1 like n times. And of course, we have no idea what the value of f1 is. But let's fix it as some constant c, which we will determine later on. So this f of n is actually c times f1, which is, c times n, f1 times n. And since c is equal to f1 by our definition, so this is actually c times n. And the next trick we are going to use is, okay, now we recovered kind of the value of f for all these integers. Now we want to go into the next best thing is rational numbers. And we know for a fact that you can add rational numbers enough number of times to get an integer. And then for integers, we already know what f is. So that will help us deduce what the value of f for rational numbers is. So if x is equal to p over q, then we can add x q times to get an integer. So that's what I have here. So f of p is equal to f of p over q plus f of p over q added q times. Then I take the f out kind of. So f of p over q plus f of p over q times, and which is exactly q times f of p over q. So right here, we use the fact on the left-hand side that f of p is just c times p. So that gives us c times p is q times f of p over q. And it implies I have made a LaTeX typo there. So it should be f of p over q. So moving the q to the left-hand side, we have f of p over q is equal to c times p over q. So in particular, what we have concluded is if I took any rational number x, f of x is equal to cx, any positive rational number. I mean, if you had this functional equation for all the real numbers, of course, I wouldn't have to say positive rational number, but here in this case, we are really fixated on the positive real line. But in any case, this works out. And here, typically you'll have to use some sort of continuity assumption, because otherwise this functional equation that we have right here, f of x plus y equals f of x plus f of y, like you can find other solutions, like look some sort of like using axiom of choice and like some sort of set theoretic jugglery. You can actually find other solutions to this equation if you don't demand something like continuity or so on. Here we kind of don't have to. We have monotonicity, and that is good enough. Because what we get is like any real number really can be sandwiched by a sequence of rational numbers from above and a sequence of rational numbers from below. And how do you do it? Like we all know that like a real number has a decimal expansion. So all you do is terminate it at some point. So that will give you some big integer divided by 10 to the n, some rational number like that. And we all know that that converges to eventually to that real number. And similarly, you find like you just increase the last digit by 1 or something so that you converge from above. So you have two sequences of rational numbers. And for each of them, you have c times x and c times y. So if xn converges to r from below and yn converges to r from above, then cxn has to go to cr, cyn has to go to cr. Like you cannot really converge to two things. Like actually, I shouldn't be using the word convergence, but about monotonicity. I mean, you cannot have two real numbers sandwiched between two things that are really going to like one real number. Yeah, so that kind of tells you that for all real numbers, this function is f of L equals c times L. So what this tells us is that expectation we cared about, E of x. So if you had a needle of length L, you threw that on this parallel strips of wood, and this was the average number of times you are intersecting like the line. So that just becomes a linear function of L. But still, that does not really tell you a formula because we don't really know what C is. So the next goal will be figuring out C. Yeah, so earlier we had deduced that expectation of X is only a function of the length when considering polygonal wires. We had taken like lines to finite number of like line segments together or needles together. And we had seen the additivity property. But this also extends to curved things, like not just piecewise linear things, but things which are overall like very nicely, smoothly curved, or maybe they have a few kinks here and there. But overall, they're like mostly smooth kind of curves. You can use an approximate argument, right? Like you can approximate this kind of smooth curves by just sampling them like at like some sort of equal distances, and you get a polygon, and you take more and more samples, you get like polygonal lines with more and more like smaller line segments, and eventually it reaches a limit, which is the smooth or nice curve. So this kind of statement still holds as long as the length of that curve is L. Doesn't matter whether it's linear or like piecewise linear and so on. Then we know that this expectation is actually C times L. Now, let's consider a nice figure. So a circular wire of diameter D. D, remember, is the width of those parallel like strips, the strips we had. The width of each strip is D. So now we are considering a circular wire of diameter D. And the circumference of this circle is pi times D. And the circumference is precisely the length of this wire, you could say, right? In this case, actually finding the expectation is almost trivial. Like you know right away what the number of intersections is going to be. Like in like almost all cases, actually in all cases, it's going to be exactly 2. So I've shown 2 cases. One is where it intersects. So the width is D, so it cannot really like cut across 2 lines. So it has to intersect twice here. And then when it's tangential, it also kind of intersects twice. Although that's also very like negligible, like what we would say like a probability 0 event. But still, like even in that case, it has like 2 points of intersection. So the expectation of a constant random variable, like this random variable this expectation of X is going to be 2, right? Because it's always 2. The number of intersections is always 2 in this case. So there's no fancy computation to do here. So what we get from that formula is, so if you remember, f of L was C times L. So L here is pi D. So you have C times pi times D. And that is expectation of X, which is 2. So C times pi times D is 2. So we actually figured out what this constant C is. So C is actually equal to 2 over pi times D. So I see this is Cauchy's functional equation. That's right. Yeah. So we are, yeah, I'm just reading out the questions in the chat. So we're trying to compute the probability of the needle intersecting once. In this case, actually, we are looking at the case like L less than D. So if you remember, yeah. So in that case, at least you can yeah, you can intersect at most once. Yeah, and this expectation gives you the probability of the needle intersecting once. But if we actually went for longer needles, so what this procedure will give us is, I don't know if I can draw here. Okay, anyway, I don't think I can draw.
You should
here.
be able to draw if you go to the top of the screen and click something like settings and then click annotate.
Yeah, so yeah, thanks. So yeah, so instead of having just P1, we would have P1 plus 2 times P2. And this whole procedure will actually give you this number. Like, let's say we had something which was length bigger than D, but less than, let's say, 2D. So you can have at most 2 intersections. So all this, what we did here, will give you this number. And maybe you'll have to recover P1, P2 using some other methods. But having L1 less than D kind of gives you straight away P1. So yeah, so that's what's going on here. So yeah, just to remind you, we are actually in one subcase of the Buffon needle problem. We will not really be solving the full problem. Like we'll just be focusing on this case where L like is strictly less than D, because it has such a nice interpretation. And this is actually due to Barbier. This solution, this kind of invariant kind of way of looking at things is due to Barbier. How do I get rid of this? Eraser, right? Okay. All right. Yeah, so if L is less than D, we have that this probability P1 is equal to expectation of X is equal to 2L times pi D. So now we have a few things around. We have a P1, L, pi D, and so on. So we can play around these variables and maybe express one in terms of the others. So yeah, so if we, so here we actually found P1 in terms of L, pi, and D. So we can kind of invert this problem around and write pi in terms of 2L over P1D. So L is something that's given to us, D is something that's given to us. And when we threw these needles, so P1 is something we estimated by doing some sort of like computation of, okay, we threw 10,000 times and 2,000 times we had intersections. So we compute this number like 2,000 over 10,000, it's 1 over 5, and we have all this L and D. So that kind of gives you a very physical way of computing pi by throwing needles. But at the same time, there's another way. Of course, there's probably more ways, but like there's yet another way of moving things around. And that is expressing this L in terms of D, pi, and P1. So we have L is equal to half times P1 times pi times D. So what does this tell us? That let's say we have a fixed width D, and let's say I have a figure which gives you the same value. So the probability of intersecting once no, sorry. So the expected value of X is 2. So this tells us that any wire that always intersects twice, that must have the same length as a circular wire, right? Because in the proof, we never really use the fact that, like when we deduce the value of C from the circle case, what did we need? We needed the fact that the circle had width D, because that enabled us to make sure that whenever we place a circle on the figure, it has to kind of cut across the lines. If it had length less than D or width less than D, you would have some cases where it would just fit like in a very snug way between two lines and it wouldn't intersect at all. We didn't want that. So that's why we demanded that it be length D. And the other thing is it was convex. So it intersected exactly twice. And just to remind you what a convex body is, so it's just like, just think of a disk. If you take any 2 points in the disk and you join a line between them, then the line, so let me draw a picture. Like for example, where did that vanish? Anyway, I'm not able to find this annotate thing again, but
Are you
oh yeah,
able to
here
mouse
it
over
is.
the
Yeah,
top of the screen? And, yeah.
yeah. So for example, like if I have two points here, one here, and I join them, it's completely within this body. So this is an example of a convex body. But if I take this, for example, this is not a convex body because I can take a line here, so point here and point here. And if I join them, there's some part of it which lies outside this. So for convex bodies, it is, you can intuitively think that when you put them, it will intersect a line at, if it's of width d, it is going to intersect at 2 points. And so the question becomes, is circle the really only like figure with width d? It's actually not. And in fact, this kind of gives you a theorem saying that anything which has width d has circumference pi times d. And these are what are called ruler polygons. For example, this yeah, so this, for example, you can draw an equilateral triangle and put your compass like on one of the vertices and draw an arc joining the other two. So then like this is a ruler triangle. Like for example, this is a ruler triangle and it has actually width equal to side of this equilateral triangle. And you can form many kind of ruler polygons and they actually have exactly the same circumference as a circle. And this is Barbier's theorem, which says any closed convex set in the plane, in the Euclidean plane, with constant diameter d has circumference pi times d. So you see like here, this whole argument, like we didn't really do any integration or we didn't try to find probability densities. It was just like some sort of very like um, some sort of exploiting the symmetry of the situation to find answers without doing much of the hard work. It's a very conceptual way of looking at things. And which brings us to some reflections. Like we did some transformations under which the answer to a problem remained invariant. And what were those transformations? For example, we could twist our body around. Like it didn't matter like what our shape of our body was. We could have twisted it like we made polygonal lines and so on. So this is kind of like you have some sort of invariant like number associated with this thing. And we found a distinguished object, which is a circle of that diameter. And for this object, the answer was quite straightforward. Sorry. So yes, and so in a sense, what we did was we started with a kind of very specific problem. Then we had a family of problems. We generalized this. We made it a bit abstract, not just a straight needle, but general. Then in that family, we found an object for which the answer was like obvious from the outset. And then like we just transferred that solution to the original problem. That's what we did. And that's what usually the idea of symmetry and invariance is what happened. Like you have a symmetry of a situation, you have something which is invariant. So you transform this object into something very simple for which the answer is obvious. Then you transform back to get the answer for your original problem. Yeah, and here, as a tool, we defined an additive set functional, which was this expectation of x, on the family of noodles. Noodles meaning all this some sort of twisted stuff. And this is the idea of invariant measure, like meaning you associated some number, and if you had taken two of them, it was additive over that. So in a way, I mean, I didn't define what a measure is and so on, but just think of it as something assigning a number, like a volume or area, something of that nature. Or counting is also a measure. You're measuring the size of some set. So the only property we really needed was additivity. Like that's what we exploited throughout. So to phrase it in a bit more mathematical term, to the set of finite unions of piecewise smooth, non-self-intersecting curves, we associated a valuation or measure by the name of Ex. And that kind of helped us like build this problem up. And here, by the way, I say non-self-intersecting, but that is actually not necessary if you allow for multiplicity. Like for example, instead of one needle, I could have just welded them together just right out, like to coincide with each other. So one needle becomes like two needles. But then, of course, you'll have to account for multiplicity and like add a 2 to that. If you do that, if you take care of these kind of edge cases, then I don't have to really add the phrase non-self-intersecting curves. Yeah, so having said this, I'm going to look at the chat again. Okay, diameter is the largest distance between, yeah, that's right. I never, like when I was talking about Rouleau triangles, I never really defined what a diameter was. So diameter is like, you take some sort of, yeah, so let's say you have a figure like this. It became non-convex, but doesn't matter. So you pick a direction, and then you can draw a line, and you can draw parallel lines, right? So you fix a direction, like, and draw parallel lines. So at some point, for a convex body, it will touch, like, be tangential at exactly 2 points. So the distance between these 2 parallel lines is width in this direction, kind of width in this direction. You can think of. But yeah, and if you do it in all directions, all such directions, you'll get width in, like, it will be a function of the direction actually. But if it's like constant width, it's like a constant function. So it kind of tells you that, yeah, that's what we mean by constant width bodies. Yeah. All right. Yeah, it is not. So Max said, is it the largest distance between one point to any other point? No, that is not. That is not it. It is actually like the width, I should say. Mm-hmm. All right. So yeah, so now that I talked about this valuation E of X, so I'm going to make it a bit more explicit. So I had my subtitle. So how much time do I have?
It's about 5:40. So about it's not too strict, but some amount of time between about 20 to 35 minutes.
Okay, sounds good. I think I'll be done before that. Yeah. So the subtitle of this talk was a glimpse into continuous combinatorics, right? So that's what we're going to get into. So this is like a Venn diagram, which you must be very familiar with. You have 3 sets, and typically, let's say you want to count like what the size of the union of these 3 sets is. So the naive way first you do is you just count the number of things in A, B, and C, just add them up. Then you realize, oops, I just overcounted. Like B intersection C, I counted twice. Things in A intersection C, I counted twice. And A intersection B, I counted twice. So I just subtract all of them out. But then I realized actually I subtracted A intersection B intersection C one too many times. So I have to add it back. And so this is exactly the idea of the inclusion-exclusion principle. And in terms of sets, like when I talk about measure or valuation, just think of it this way. Given a set, the way I count the size of the set is just the cardinality. And for that, we have this sort of inclusion-exclusion principle. But if you think of these as really like circles or disks in the Euclidean plane, and if you think of these numbers like absolute value A, B, whatever these things are, to be area, there is exactly the same formula that holds, right? So if I take the union, the area of A union B union C is area of A plus area of B plus area of C, and so on. And the reason for it is pretty simple, right? Because when you construct the notion of area, you start with certain atomic kind of objects, right? Like you have some sort of, like when you talk about finite sets, like each element of the set counts as 1. Like if you had n elements, like then that counts as n. But each of them is kind of equally likely, or like they have the equal weightage, so to say. So it is, so the inclusion-exclusion kind of principle kind of follows from that. So similar to that, here you have maybe some atomic parts like a very small hypercube or something like that, and these are comprised of that. So in a way, you can say like inclusion-exclusion principle for area and volume are also kind of, in some sense, derived from the set theoretic version. Like they're a continuous version of that. Like here, you just make a grid and count the number of tiny grid like things in each set, and that approximately corresponds to the area of that set. But the whole idea here is some sort of translation invariance, like a cube here and a cube somewhere else. They have exactly the same, I should say square here, because we are in the Euclidean plane. So you need like a tiny square here. If I translate it somewhere else, the area does not change. Similar to how in sets, if I permute things around, initially, let's say I had 1, 2, 3, 4, and so on. Now I moved 1 to number 10. That did not change the size of that. It's still 1. So that's the whole idea, that like there is some sort of invariance that is going on. So, so similarly, like depending on your choice of this invariant valuation, you can like do this and get really like fun formula, just like binomial theorem and all that, like you get for counting like subset sets, like different ways of combinatorial thinking. You can do it in a continuous manner. Like this was a very simple way. Like I said, there's an immediate analogy with the set theoretic notion, but you can actually talk about invariant measures on more complicated objects. In fact, in the Buffon needle problem, we have done exactly that. Although like we hid all those things under the carpet. Like if you think a bit more about it, you realize when we defined expectation and so on, we never specified what the events were, and we never, like we said, okay, I mean, there is some underlying sample space and so on. And so all of these kind of make sense, but if you're thinking very, like you're being very nitpicky, we never really defined what the events were, like where these random variables really existed and so on. But that was immaterial to the end solution because of some sort of invariance. Okay, so I'll talk more about it at the end, but before that, I'll leave you with a couple of more examples of this flavor of the Buffon needle problem and the solution we just gave. So if I have, let's say, two bodies like this, they don't have to be convex, although they are drawn like this. And if I pick a random point in C1, C1 is, by the way, the bigger one, C2 is the smaller one. So if I asked you this question, what is the probability that like a given random point in this bigger body actually lies in the smaller body? So a straightforward answer is actually if you take the ratio of the areas, and that's again follows from some sort of translation invariance of this, of assigning like probabilities. Like you don't really want to distinguish between, if you have a tiny square here or somewhere else, you don't want to give more or less probabilities to one or the other. Like they're equally likely. So this is the answer you get. But you can consider some sort of dual version of this. And by the way, if we go to the previous example, I was saying the area example is not that interesting because it is actually a straightforward generalization of counting subsets. But this is actually a bit more fancier generalization, Sylvester's theorem. So let's say you have two compact convex sets. Okay, actually somehow from C1, C2, I went to K2, K1. But anyway, actually C1 is same as K1, C2 is same as K2. Just the notation has mutated. But yeah, so here, let me draw a picture. So we still have two bodies, one convex body, which is C2 or K2. Okay, anyway, yeah, I mean, so you have this bigger body K2 and smaller body K1. Yeah, I think it's unable to bear the load of this program. Okay, so if you had this convex body within this bigger one, and let's say I asked you this question. So instead of points, I'm talking about lines intersecting things. So you draw a random line, and let's say it intersects the bigger convex body. And you ask the question, like conditional on that fact, what's the probability that it will actually intersect the body inside? And just as we figured in the Buffon needle problem that like the way, the shape of the needle didn't really affect the answer and so on, that's exactly what happens here. Doesn't matter where the smaller convex body is inside, like doesn't matter the location, doesn't matter like what the shape is. It could be an ellipse, it could be a sphere, it could be some other like a diamond or something like that. But as long as the surface, as long as the circumference is the same, the probability will actually be the same. It just depends on the circumference. So length of the circumference of the smaller body divided by length of the circumference of the bigger body. And here, instead of counting the number of points, we kind of wish to compare the number of lines that intersect K2 and the number of lines. But the problem here is the number of lines is infinite, right? What do I mean really by like comparing the number of lines that intersect and so on? And that's where the idea of the invariant measure comes in. Like, because let's say I talked about lines that pass through the origin, they typically are determined by directions, right? Like each direction kind of corresponds to a line. I'll be a bit sloppy here, but you can think of it as all those lines correspond to some sort of circle. Circle in the sense, like each point on the circle determines a direction. So if I'm thinking of the family of lines, effectively I'm thinking of the circle. And that circle has an invariant measure, which you all know. It is essentially like length, arc length, something like that. So that you can assign to the space of all lines passing through the origin. But if you take space of all lines, not necessarily passing through the origin, you'll have another component, which is translations, like a line passing through origin, which is translated away. So that is what we would call a combination of a circle, which is like a compact kind of set, like bounded and very nice kind of set, but R is like an unbounded kind of thing. So you get this set S1 cross like Cartesian product R kind of thing. And you have an invariant measure, like on R you have the length, on S1 you have the arc length, and they put together will give you some sort of invariant measure. And that is the actual number you'll be counting. Like you'll be counting like subsets in that sense. So the number of lines is kind of replaced by this some sort of invariant measure. And it is a theorem that it's unique up to scaling. Like whenever you give me some sort of counting measure, I can always multiply it by 2 or something. It will still like satisfy similar equations and so on. Just that like instead of having a formula, you'll have 2 to the n times that formula or something like that. So yeah, so that is what I mean by number. That's the measure. And another, like the same approach of using invariant measures and so on can be used to prove the isoperimetric inequality in the plane. And what is this isoperimetric inequality? By the way, if you like kind of split this word isoperimeter, it's kind of like iso kind of means like equal, and perimeter means the kind of the boundary of a closed curve. So if you fix this length L, and that's a family of isoperimetric stuff, closed curves, and you care about the area enclosed by this curve. So what the isoperimetric inequality kind of tells you is that the area of this curve is maximized when this curve is actually a circle. And like, of course, this is a very old problem, and like this is in fact true in higher dimensions, although I don't know if there is an kind of this continuous combinatorics kind of proof that probably is, but I don't know of it. So this is actually true in high dimensions. Like if you specify some sort of surface area and so on, like the thing with maximum volume would, for example, be the sphere. And that again leads to some other inequalities like Brun-Minkowski inequalities, like some buzzwords in convex geometry. But yeah, but here, like one strategy in proving this is actually you have this curve, gamma, let's say, and what you do is take this family of lines I just described. And the function you really care about is given a line, how many times does it intersect this curve? So in fact, the arc length of the curve can be expressed as an integral of the number of intersections of gamma and an arbitrary line. And this integral is actually over the space of all lines. I mean, forget the technical word oriented, but effectively, like I said, like all lines in R2, for example, is effectively is the space, the circle, Cartesian product, the line. So S1 cross R, as we say it. So you're integrating over that space effectively. So, and this function, like I said, to each point in this space, which is a cylinder, S1 cross R is like a cylinder. So on this cylinder, like circle times the real line, you're moving the circle along the real line. So on this cylinder, this function is actually an integral valued function, because you see it says the number of intersections of gamma with an arbitrary line. So each point on this cylinder corresponds to a line, and each line intersects this curve at integer many points. So in fact, like what we have is some sort of integral over this space of over this cylinder of integer valued function, and that kind of gives you some sort of like nice way of describing the length of the curve, and then you optimize based on that, just as we kind of twisted things around with the Buffon needle problem. That's the basic idea. Yeah, and then I'll kind of try to close the loop a little bit. So instead of like doing this conceptual way of finding the solution to the Buffon needle problem, we could have gone the brute force way, like we compute probabilities. So what we do is throw this needle. So the rotation, like this needle has an angle of rotation, and the midpoint of the needle has some distance from the lines. So, and by this uniform throwing assumption, this angle theta is probably uniform in 0 to like 2 pi, and this distance of the midpoint of this needle is also uniformly distributed. So based on this, you can start doing some computations, and then here I write, since the needle crosses a line, if this distance of the midpoint is less than or equal to L over 2 sine theta, so this integral of this density becomes like this, and you actually find the same formula. So what's really, like, why do these two methods really give the same answer? That's because, as I was telling you previously, like in our original solution of the Buffon needle problem, we never talked about what the sample space was. We just used the invariant properties. But on the underlying, we were talking about the space of, like, some sort of space of lines and those kind of things, and they had an invariant measure. So that made our arguments on very firm ground, although we didn't know that. So these integrals are effectively what, like in the previous section, I was defining integral over all lines and space of all oriented lines. This is exactly what's going on right here. You are integrating actually integers, 1, 2, the like. This 4 over pi d term is actually just a the constant which makes this invariant measure some sort of scaling factor. But in effect, this function is actually just 1, right? Like if you look at the integrand here, it's just a constant function. There's nothing going on there. So like ones and zeros effectively. That's why this domain is not the full integral. That's why you have restriction to L over 2 sine theta and so on. But it is an integral over the space of all lines effectively. And that's why the argument just worked out, because there was some sort of invariant measure there. So yeah, I mean, you don't necessarily have to do the hard way, but yeah, knowing that this exists, like you can argue very conceptually and don't really have to do any computations. Yeah, I should have included another slide here, but I'll say it anyway. And I think I have probably 5 minutes or so. Is that right?
Yeah, it's flexible. If you want to go a little over, that's fine. But sometimes some people have to leave around.
Okay, yeah, I mean, in any case, I think this is the whole framework of ideas that I was going to say. Maybe I'll just wrap up, and then if there's any time like for questions and so on, then yeah. So yeah, I mean, just summarizing what we did, like we took average number of intersections of a needle of length L less than D, and we found it was 2L over pi times D, and we moved things around and proved a few results like Barbier's theorem and all that. And then looking at the isoperimetric inequality, which is actually integrating appropriate integer valued functions. Typically, when we talk about integrals, we always think, okay, nice real functions and so on. But integrating appropriate integer valued functions can lead to very nice insights to very like continuous kind of things. And then this is like a Zen kind of thing, which I always like to say, to find what changes, first find what does not. So always first look for symmetry and invariance in whatever problem you're studying, and some sort of like, and sometimes it does help to solve a harder problem, which has the right like germs of the original one. And then I'll just end. And by the way, most of this was based on like a book by Giancarlo Rota, which is called Introduction to Geometric Probability. And maybe some of you, if you take up maths in your undergraduate studies and so on, it's a fun book to read, and it's very readable actually. And he's a very good writer, by the way. So yeah, I mean, I'm just going to end with a quote that mathematics is a study of analogies between analogies. So I think he always tried to stress on that. So the more you see commonality, the better mathematician you will be. So I think I'd like to end on that. So if there are any questions, I'll take it.
Thank you so much for that talk. I thought it was super interesting. So
Yeah, I think some
Yeah,
things.
so if anyone has any questions, feel free to put them in the chat.
Yeah, I mean, if there are no questions, like you can like write on the chat box as I kind of narrate, like one just last point I wanted to make. And that was, um, I was talking about the space of all lines, and in higher dimensions, you can do similar things like space of all hyperplanes, or space of like k-dimensional planes in n dimensions, and so on. And there, actually, it's a theorem. It's a kind of uh, yeah, a bit involved theorem, you could say, that all these spaces I'm talking about actually have an invariant measure. So that needs a proof. There's a kind of averaging kind of procedure. But once you know that, like once you know that there is an invariant measure and so on, this the kind of argument that Barbier did, you can just directly translate to many different types of problems. So so effectively, like that is my main point. Like our argument did not care about the foundation; it just went with intuition, but the foundation is there. Okay.
It looks like there aren't any questions, but
Sounds good.
it looks like everyone really enjoyed the talk, so thank you so much for coming.
No problem.
And then to everyone here, we'll probably be taking somewhat of a hiatus for virtual masterful over the summer, because I know a lot of people's schedules are going to be different, including mine. So we'll probably take some of a hiatus. There might be some talks still, but for instance, we probably won't have one next week, but we will see exactly what happens with that. I might end up asking in an email how much interest there is in doing it over the summer still. All right. So thanks to everyone for coming.